everybody.
Good morning.
Good morning.
Good morning, sir.
Okay, so we are in the last session of approximation theory. What we have done? We have done one approximation, that is variational principle, and in variational principle we have entirely different approach where we have just parameterize our uh, we have just optimize our parameter of a wave function, and we can get the using we can just use the maxima and minima, and we can get the energy eigenvalue for the lowest energy, so lowest state of any system. Second, we have just gone for WKB approximation. It will just tell you all about how your phase space in a quantum mechanics is quantized. If you want to be remember one liner, that area under the phase space is quantized, and we have different kind of quantization rule. And we have also learned how transmission probability, that what will be probability that particle can go into classical forbidden region. We have also done this story. And then we have go for perturbation. It is mainly dependent on Taylor expansion. And the beautiful part is that on the knowledge of original Hamiltonian, we can analyze the perturbed Hamiltonian with the help of Taylor expansion. So in last two sessions, what we have done, we have just done the non-degenerate perturbation. Why we are saying it non-degenerate perturbation? Because that energy eigenvalue of H naught is non-degenerate. They are different. Now, today we are going to discuss with degenerate perturbation theory. So before going to degenerate perturbation theory, I am just going to recall how we can diagonalize any matrix or any matrix. So this is the ultimate thing we have to do again and again into this problem. So just I am giving you a very small example how we can go for the diagonalization. And once we will go for the diagonalization, then we can easily solve each and every problem of this particular topic. So suppose we have a matrix A. Let's say this matrix is A, and this matrix is 3 cross 3 matrix, and we have 1 0 0 0 0 1 0 1 0. What I want, I just want to diagonalize this matrix. So how you will diagonalize this matrix? You have to diagonalize this matrix in a basis of some matrix. So the best basis is nothing but the eigenvector of this particular matrix. So what is the first step behind that? The first step behind that we have to find the eigenvalue and the eigenvector. What I suggest you just find the normalized eigenvector such that if we have a basis matrix and normalized as well as orthogonal eigenvectors, such that this basis matrix will treated as a unitary matrix. So what is beautiful part of unitary matrix? That U inverse is equal to U. So you need not to calculate U inverse once you are going to calculate U. So we will just use this concept. So let me try this, and then I will explain what I am going to do. And always we try to write our matrix, the basis matrix, as a symmetric term. Why? Because if you are writing in a symmetric term, the unnecessary calculation can be avoided. So let me give you the example. So suppose this is a matrix. I know that eigenvalue is 1, 1, and minus 1. So these are the eigenvalue. And let's say this is lambda, this is lambda 1, this is lambda 2, and this is lambda 3. And what will be eigenvector? So if you were going to calculate eigenvector, the eigenvector we can find, this is phi 3 as 0, 1 by root 2 minus 1 by root 2. You can easily find this eigenvector. I have discussed in our tools also. And we can have eigenvalue vector according to 1 and 1. We can choose this eigenvector, that phi 1 is equal to 1 0 0 and phi 2 is equal to 0 1 by root 2 1 by root 2. So these three eigenvectors we have calculated with ourselves. Now what we will do, we will construct a S matrix, some S matrix, and that I will try to make this S matrix as a unitary matrix. So I just construct S matrix in a basis of phi 1, phi 2, and phi 3 because they are eigenvectors of matrix A. And we have done this eigenvector. So if you have any confusion, just go to your tools class where we have discussed it very nicely. So what is this S matrix? I will construct my S matrix such that this will be 1 0 0 0 1 by root 2 1 by root 2 0 1 by root 2 1 by root 2. So this is my S matrix. To diagonalize this A matrix, what we need to calculate? We need to calculate S inverse. So what I have done, and this will be minus, this is minus, okay? What I have done, I have write my S matrix very efficiently such that you can see these are the symmetric matrix. Some people can write this column here and this column here. It will also works. Some people write this column here, this column here. It will also works. But what will happen if you will write not in a symmetrical form, then you need to calculate S inverse. There will be change in sign plus and minus. So what I have done with my previous experience, I have written my S matrix as a symmetric form. What I have done, I have taken this matrix as an orthogonal and these are normalized also. So what I will find, this S inverse will be exactly same matrix. So what will the idea? You construct S matrix such that S inverse will be same. So S will be same, S inverse will be same, and if you will check, the eigenvalue of S and S inverse will be plus and minus, as well as they are just like as a unitary matrix. They are something called rotational matrix of pi by 4. This kind of situation is there. This is so rotational matrix just treated something like this. Okay, so I am not going very deep inside. Now you please remember, we have constructed this S matrix such that eigenvalue of first column is 1, eigenvalue of second column is also 1, and eigenvalue of third column is minus 1. So you have to just remember this thing. If you are going to calculate some matrix that will be diagonalized of A matrix, so let us write A diagonalize. AD is the something called diagonalize, and this matrix is equivalent to S inverse AS. And once you will calculate this particular thing, so I am just leaving calculation for you. 1 0 0 0 1 by root 2 1 by root 2 0 1 by root 2 1 by root 2. A matrix is 1 0 0 0 0 1 0 1 0, and you have another matrix that is will be S. This is S inverse, so S will be again same. So 1 0 0 0, sorry, 0 1 by root 2, 1 by root 2, 0 1 by root 2 minus 1 by root 2. Can you please tell me without calculating? I will suggest you just to go and home after this class. You can just do the practice for calculation. But without calculating, can you please tell me what should be that matrix? The diagonalized matrix? Can anybody tell me?
diagonal element eigenvalue.
The diagonal matrix will be eigenvalue, but in which order? In which order? Where is 1? Where is 1? Where is minus 1? Can I get this kind of thing? 1 minus 1 1, this kind of thing?
No, sir.
Or 1 1 minus 1? Which kind of thing you will get?
1 1
Or
minus.
minus 1 1 1? All are diagonalized and all are eigenvalues. So which will be the diagonal term?
1 1 minus 1.
1 1 minus 1 exactly is in a basis in which you are writing the S matrix. Are you getting this thing? Exactly in a basis, the S matrix is written 1 0 0, the eigenvalue is 1, 0 1 by root 2 1 by root 2, eigenvalue is 1, 0 1 by root 2 1 by root 2, eigenvalue is minus 1. And you can also see the symmetry. You can see the symmetry. After 1 0 0 0 0 is here. Here is also, and here is also. So what we have done, we have written our S matrix such that it will superimpose to A. And this is known as the block diagonal term. This is the block diagonal matrix, and we have written our S matrix such that if it is block diagonal, then it will be also block diagonal. Such that this will be surely come to this one. And what will be the answer? According to this S matrix, if I am taking this S matrix 1 1 minus 1, then my answer will be 1 0 0 0 1 0 0 0 minus 1. So there is no need to calculate these all things. You have to do practice one or two problem with yourself and make yourself confident such that you can directly use this particular concept to solve the degenerate perturbation theory. If you have any doubt, you can just ask me. I will just leave this thing to up to you so that you can just go for this. I think you have done this thing into mathematical physics also, isn't it? So are you people comfortable?
Yes,
How we
sir.
are going to diagonalize this particular matrix? Okay, so let's go for a degenerate perturbation theory. So this is a very interesting, and the role of perturbation is actually in the degenerate perturbation. Let me explain you with some problem, then we will discuss what we are going to do.
सर
बोलो।
सर जो हमारा इनवर्स है सर वो मतलब आइगन वेक्टर से निकल के सर वो सेम ही रहेगा बिल्कुल इनवर्स उस मैट्रिक्स का ऐसा
अगर आप एस ऐसा लेते हो तो, है ना? अगर आप एस सिमेट्रिक मैट्रिक्स लेते हो तो आपका टाइम काफी बच जाएगा ना। आप ट्राई कर सकते हो। व्हाट यू विल डू, यू विल टेक एस, जस्ट टेक अ टाइम, थोड़ा सा टाइम ले लो। एक बार एस 1 0 0 0 1 बाई रूट 2 1 बाई रूट 2 0 1 बाई रूट 2 माइनस 1 बाई रूट 2 ले लो। तो दिस इज योर फर्स्ट चॉइस ऑफ एस। सेकेंड चॉइस में आप एस ले लो 0 1 बाई रूट 2 1 बाई रूट 2 1 0 0। ये भी आपका शायद सेम ही रहेगा। दिस विल बी अगेन रिमेन सेम बिकॉज दिस इज ऑल्सो सिमेट्रिक। थर्ड चॉइस में आप चाहो तो ले लो, थोड़ा सा चेंज करते 1 0 0 1 बाई रूट सॉरी 0, 1 by root 2, minus 1 by root 2, 0, 1 by root 2, 1 by root 2. आप यहां पर देखोगे कि your S inverse will be change. Okay, but I think in first and second your S will be remain same. Sorry, इसमें भी नहीं रहेगा. Yes, इसमें भी शायद मुश्किल हो. इसमें भी नहीं रहेगा. Yeah, you can just check it. You can just check it. Okay. So best way is that always choose S as your symmetric matrix. Okay, and your eigenvalue must be orthogonal. So in a physics, it will works. But I don't care about mathematics right now. कि पूरा mathematics में क्या होगा? But in a physics, in a real system, it will works. Okay. So anyway, let me just try to go for. And the best thing is that in the diagonal term, you will get the eigenvalue. But what is the eigenvalue in the diagonal term will be depends on how you are taking the S matrix. Anyway, so now in the non-degenerate perturbation theory, what you can see, if I am calculating psi n1, and this will be m is equal to not n, and here is phi m, w phi n, and you have en0 minus em0 and phi m. Remember, we have done this thing into last class. Now, if n and m are same, suppose there is degeneracy, then this value will be go to 0 and psi n is not defined. So psi n1 is not going to define. So it is a big problem. It's a really big problem. So if you have degenerate eigenvalue of h naught, then how you will approach? What should be that? So what we will do, we will just try to write each and everything in a basis in which h naught is diagonalized. And then we will just go for the next level, whether we will see that degeneracy is breaking or not. If degeneracy is not breaking, we cannot do anything. We have to go for the further perturbation. So let me go for what is real problem. Real problem you will see. What is the real problem of degeneracy? Suppose the eigenvalue of any operator is, let's say, Hamiltonian E naught, and minus E naught. So the real problem is you have eigenvalue E naught, and minus E naught. So actually physical measurable quantity is E naught and minus E naught, but you have three space associated with E naught and minus E naught. One is for first E naught, second is for second E naught, and third for is minus E naught. But in a mathematical term, what you will see? You will see there is two-dimensional space, because you cannot say which eigenstate is associated to this E naught and which eigenstate is associated to this E naught. So what will happen? You will be confused such that you are working into two-dimensional or three-dimensional system or not. Once you will introduce the perturbation, this degeneracy break and three-dimensional system or three-dimensional space will be appeared as three-dimensional. Let me give you an example, then we can only understand how we are breaking the degeneracy actually. Let me give you the example. And before that, what should we have to do? The first thing, we have h naught. This is my h. H will be h naught plus lambda w. This is my Hamiltonian. And here h naught is your degenerate eigenvalue. So what is your first step? Your first step, diagonalize h naught. So you have to diagonalize h naught. So in which basis you will diagonalize h naught? Can you please tell me in which basis you will diagonalize H naught?
H naught के basis में जी.
No, no. In which basis you are diagonalize H naught? The eigenvector of H naught. You can make sure that the eigenvector of Hamiltonian will be orthogonal or orthonormal such that you can easily diagonalize H naught in the eigenvector of H naught. So what you will do? You will just diagonalize H naught in basis of eigenvector of H naught itself. Let's say that matrix, so you have H naught D, and this is your H naught D is equal to S inverse H naught S. And if H naught is not diagonalized, then it's okay. It's very good for you. There is no need to do this particular thing. Second thing, once you will diagonalize this H naught, what you will do? You will write W in a basis in which H naught is diagonalized. So what you have to do, you have to write W in a basis in which H naught is diagonalized, and let's say that is W dash, and W dash in which basis H naught is diagonalized? In a basis of S. So you have to write S inverse WS. So if, here is one more thing, if H naught is diagonalized, then W dash is equal to W. There is no need to find W dash. That will be W. Why I am claiming this thing that W dash will be W if H naught is diagonalized? Why I am claiming that this will be same?
सर जो आइडेंटिटी मैट्रिक्स आएगा हमारा वो
Very
इसमें
good.
सेम रहेगा.
Means if H naught is diagonalized, then this S matrix is an identity matrix. So if you will write anything in your identity matrix, that will be the same thing. So there is not any problem, isn't it? So why? There is no need to do any work here. And third, and the last thing, diagonalize W dash in a basis of eigenvector of, so you will get eigenvector of W dash, that is you will find W dash D is equal to some new matrix. This will be new matrix U W U inverse W U. So it is not appeared now. So you will find W dash D is equal to U inverse W dash U. U is written in a basis of eigenvector of W dash. So what you have done? You have diagonalized each and everything. So now we have H is equal to H naught diagonalize plus lambda W dash diagonalize. So you have diagonalized this thing, you have diagonalized this thing, all are diagonalized, you can easily get the eigenvalue, isn't it? If the matrix is diagonal matrix, then there is not any problem. You can easily get the eigenvector. Are you getting this thing? If you have any doubt in any step, then please tell me. The idea is that if you simultaneously diagonalize H naught and W, then you can overcome with that degeneracy. That's it. This is the main idea. And it works actually. Look at here. Because if you are diagonalizing the any matrix, you are just writing the equivalent matrix. Some in some another basis. So you are not changing the matrix. Why? After the diagonalization, the eigenvalue will remain same. So we are just using all this basically concept to understand our system. Let me go for this particular example, some example, then you will see how we can go for different types of problems. So we have three type of problems. The first problem is very trivial, where H naught is diagonalized and W dash is not diagonalized. Second problem you will find where H naught is not diagonalized. So you need to find the W dash, and fortunately this is also diagonalized. W dash itself will be diagonalized. So this is the second type of problem. And third type of problem, you have to first construct H naught in a diagonal form, and you will find that W dash is not diagonal, and then you have to diagonalize W dash. So there are three type of problems. The third part is the most interesting. First two are very trivial and very simple. You can just go for mathematics and you can do this problem. So let me go for first problem, and you can easily give the answer without solving the problem. This is the thing. If you know the matrix, what is eigenvalue, eigenvector, you can easily do this thing. But I will do step by step each and everything. Anyway, so I think you are comfortable up to this.
Yes, sir.
Okay. So let's go for this problem. This is a very nice. H is defined as E naught 0 0 E naught plus lambda, and this will be 0 V naught 0. Now, so what you have to do? You have to, using the degenerate perturbation theory, you have to find the eigenvalue after the perturbation. So it's a very simple. Now, what is the eigenvalue here? E naught and E naught. This is the degenerate. So you have eigenvalue E naught and E naught. This is the diagonal matrix. So you can have eigenvector phi 1 is equal to 1 0, phi 2 is equal to 0 1. And hence they are diagonalized or not diagonalized? They are diagonalized. So there is no need to diagonalize H. So this is your H naught plus lambda W. This is your W. So hence H naught is diagonalized. Hence H naught is diagonalized. Then H naught D is the same thing. You are writing E naught 0 0 E naught. Now can you please tell me what will be your W dash? What will be your W dash?
G0
Anybody?
V naught.
W.
That is same W. Why it is W? Because let me give you the explanation also. W dash is equal to W, and this will be 0 V naught V naught 0. Why it is there? Because H naught is diagonalized, and it is diagonalized in a basis of phi 1 and phi 2, and phi 1 and phi 2 is 1 0 and 0 1. So what will be S matrix? S matrix is 1 0 0 1. isn't it? And what will be S inverse? S inverse will be also same. This is identity matrix. And if you are going to calculate S inverse WS, then you will get the W. And this is your W dash, and you will get the same matrix. You will get the W is equal to W dash. You can easily check it. So unnecessary, we need not to do this type of exercise. We know that this is diagonalized, then W dash is equal to W. What will be your next step? Just tell me, what will be your next step?
Diagonalize W dash.
Diagonalize W dash. So now we have to diagonalize W. How you will diagonalize W dash? You will just find the eigenvalue and eigenvectors. So let's go for diagonalize W dash. So what will be W dash? W dash is 0, V naught, V naught, 0. So what will be your eigenvalue? Eigenvalue is V naught minus V naught. What is eigenvector? Eigenvector is 1 by root 2, 1, 1, 1 by root 2, 1 minus 1. You can just check these are the eigenvectors. And so we will construct a U matrix. That U matrix is 2 cross 2 matrix. I will write 1 by root 2, 1 by root 2, 1 by root 2 minus 1 by root 2. And what will be U inverse? U inverse will be remain same. That is 1 by root 2, 1 by root 2, 1 by root 2 minus 1 by root 2. What we have to do? We have to just diagonalize W dash. D is nothing. U inverse W U. Can you please tell me what should be the answer?
Sir, B naught 0 0 minus B naught.
Minus V.
Very good. So you will just get it V naught 0 0 minus V naught, because I know that eigenvalue according with this matrix. Sorry, this matrix is V naught and this is minus V naught. So this will be the thing. If you will write this one here, then obviously this minus V naught will be there and V naught will be there. So what you have done, you have just diagonalized W dash. And once you are going to diagonalize W dash, then everything will be sorted out. And let's try to get the final solution. So we have H as H naught diagonalized, it is given. So this is E naught 0 0 E naught plus we have lambda, and this will be W dash diagonalized. So this will be V naught 0 0 minus V naught, and this is something like H is equal to H naught diagonalized plus lambda W dash diagonalized. This kind of situation is there. So what will be eigenvalue? So there is two eigenvalue. One is E naught plus lambda V naught. Another is E naught minus lambda V naught. That's it. So what is going to happen? What is physics behind this? The physics is very interesting. You can just take this physics. Before the perturbation, you have only eigenvalue E naught. But this eigenvalue E naught is basically 2 times E naught. But you will see that only one E naught is there. So this is the before perturbation. So you will just give some extra field, extra potential. What will happen? This perturbation is going to break down. And what will happen? You will get the 2 eigenvalue. And one eigenvalue is E naught plus lambda V naught. Another eigenvalue is E naught minus lambda V naught. So what will happen? Due to perturbation, due to degeneracy, the space was 2 cross 2, but we are getting only one this state. We are confused that which state is associated to which E naught. But what will happen? We have so beautifully perturbed this particular system, disturb our system, such that it will break into 2 parts, and 2-dimensional space will appear me as 2-dimensional space. if it is two dimensional, then we need basically what will be eigenvalue of first dimension and what will be eigenvalue related to second eigenvector. But here, due to degeneracy, we are confused. So degeneracy is broken. And we have extra information of a system due to some perturbation. So why you will see this thing can be treated in atomic physics and all about the fine structure, hyperfine structure. Everything can be discussed with the breaking of degeneracy. So this is the thing. So means what is meaning of that? Here itself there is two eigenvalue, but we are not able to see it. So what we will do? We will just check the system and then we will see, okay, there are two different eigenvalues. Are you comfortable?
Yes, sir.
If you have any doubt, you can just ask me. Okay, let me go for next problem.
एक्सक्यूज मी सर
हाँ बोलो.
सर 3 डायमेंशन में यूनिटरी मैट्रिक्स कैसे लिखेंगे सर थ्री
अभी
डायमेंशन
अभी 3 डायमेंशन नहीं कर रहा है. डोंट वरी, 3 डायमेंशन नहीं कर रहा है. ठीक है. So I am going to second type of problem. So this is very trivial, very simple. You have nothing to do. Everything is given. You have to just find the eigenvalue of W dash. That's it. What we have, let's say this is E naught 0 0 0 0 E naught 0 E naught 0 plus lambda V naught 0 0 0 V naught V naught 0 V naught V naught. Now this is the actual problem I am looking for. So this is your H matrix. Obviously, H is equal to H naught plus lambda W. So you can identify this is your H naught, this is your W matrix. And this is really good problem. But okay, so what you can see is that H naught is diagonalized? No. So H naught is not diagonalized. H naught is not diagonalized. So if H naught is not diagonalized, what you have to do? You have to just diagonalize H naught. So you have to just find that eigenvalue and eigenvector. And you know what is the eigenvalue? अभी तुरंत निकाला था. The eigenvalue is E naught minus E naught. And what will be the eigenvector? This will be first E naught के लिए 0 0, second के लिए 0, 1 by root 2, 1 by root 2, and for this 0, 1 by root 2, minus 1 by root 2. So we have just get this particular eigenvector. You can have different eigenvector about this E naught also, we remember, but we will take the simple one because the purpose is just diagonalizing it. So can you please tell me what should be my S matrix? So we have to diagonalize it. So I will define my S matrix as 1 0 0 0 1 by root 2 1 by root 2 0 1 by root 2 minus 1 by root 2. And you will also get this is my S inverse. Don't worry, this is my S inverse. So what you have to do? You have to just go for H naught diagonalize, that will be S inverse H naught S. This is your H naught diagonalize S inverse H naught S. So can you please tell me what will be the solution without solving this one?
Elements are E node minus E node.
Very good. The diagonal element will be, because you know this is the eigenvector of E naught, this is the eigenvector of E naught, and this is eigenvector of minus E naught. So you will just write, you can directly write this thing as E naught 0 0 0 E naught 0 0 0 minus E naught. Very simple. Now, what is your next target? Next target, we have to find W dash. In which basis? In which basis where H naught is diagonalized? So we have to write W dash in a basis of S itself. So what will be W dash? W dash is equal to S inverse WS. So I am just giving you 30 seconds. Please try to calculate this one. You cannot guess here. You cannot guess here. You have to calculate here, because it is not necessary that W dash will be diagonalized. It may be diagonalized, it may not be diagonalized. So it is not necessary. You have to calculate it. This is very interesting. I am just writing it again. It is not necessary. Necessary that W dash is diagonalized. It may be diagonalized or it may not be diagonalized. So please calculate it. Please calculate it. Take a 30 to 35 second, 40 second and calculate it. And give me answer. Because I want you should feel the calculation. Take your time, and please calculate it yourself. I know the solution, but I wish that you can just calculate it. Anybody have done this calculation? I think your answer will be something like V naught 0 0 0 to V naught 0 0 0 0. Isn't it? If you will calculate it, I think you will get this answer.
So B to be not 0.
Very good. In a diagonal term, isn't it? In a diagonal term. So what will happen? Fortunately, you have diagonalized your W dash also. Now, please tell me, I am writing here, it is not necessary that W dash is diagonalized. But here W dash is diagonalized. Can anybody tell me why it is diagonalized? It is a fortunate. It is fortunate. Everywhere it is not going to happen. In the next problem, you will see it is not going to happen. But right now, why it is W dash is also diagonalized in a basis of H naught, in a basis of matrix in which H naught is diagonalized. Why it is happening? Can you please tell me? Why it is happening? I think you have done all your matrices and all kind of thing. Why it is happening? That W dash is also diagonalized. We just save one step. This is fortunate that we have taken so beautiful this perturbation such that it is also diagonalized in a basis of H naught, in a basis of matrix in which H naught is diagonalized. Why it is happening? Can anybody give me the intuition?
Due to unitary
So diagonal
matrix.
element.
No. Unitary matrix is not there. Why? Why? Because the eigenvector of H naught, sorry, eigenvector of W dash will also eigenvector of H naught. This is fortunate. This is so fortunate that eigenvector of this matrix will be also eigenvector of this matrix. Can you please tell me what will be eigenvector of this matrix? Sorry, eigenvalue. Eigenvalue will be V naught 2v naught and 0. And what will be eigenvector is 1 0 0, and 2v naught is 0, 1 by root 2, 1 by root 2, and this will be 0, 1 by root 2 minus 1 by root 2. So you are very fortunate that these two have same eigenvector. So why actually W dash is also diagonalized. So it is fortunate. It's a matter of luck. But in general, it is not necessary that in which basis H naught is diagonalized, W dash is also diagonalized. We will see in the next problem. We will just try to do this thing. So what will happen? We are enough lucky that we get W dash is diagonalized. So let's go for the, so we have just, so this is nothing but W dash here is basically W dash diagonalized. So what I can do? So I will just go for next level, and we will just write the answer, and you will see how the perturbation works. And this will be E naught 0 0 0 E naught 0 0 0 minus E naught. This is nothing but H naught diagonalized, and luckily we have W dash diagonalized. In the next problem I will do in which W dash is not diagonalized. So W dash diagonalized is basically you have V naught 0 0 and lambda is there 0 to V naught 0 0 0 0. And what you will get? You will get three levels. Now if you will get the eigenvalue, so before the perturbation, even if this is 3 cross 3 matrix, but we are able to identify only two eigenvalue. One is minus E naught, another is E naught. But once we are getting this perturbation is so beautiful that it will, the ground state remains same, but the first excited state will be divided into or break into two part, and this will be E naught plus lambda V naught and E naught plus lambda 2 V naught. And what will be eigenvector is 1 0 0 about this, and for this is 0 1 0, and for this is 0 0 1. Something, this kind of thing is there. No, some different. This will be basically 0 0 1. You will just calculate, and for this one you have 1 0 0, and for this one 0 1 0. You can just calculate the diagonal term. You can easily get this thing. So what you have seen, that before perturbation the information is hiding. We have three-dimensional space, but we are not able to identify all this three-dimensional space. But what will happen? This perturbation, this field is so beautifully designed such that we can have, we can break this potential. And where you are breaking, this is so sensible that this is non-degenerate, and it is just keep this thing as non-degenerate. And here is doubly degeneracy, and it is just splitting it exactly into two parts. So this is all about beauty of this type of perturbation. So I think this is my first level we have achieved into this perturbation, and then we will go for the actually what we need to do in the after the break and the next session. Okay. So if you have any doubt, you can just ask me. So just take a break of 5 to 10 minutes so that I can clean the board particularly. Then we will go for next level of 2 and 3 problem. Okay.